So this talk is slightly different than what you have seen previously. And if you have any questions, we can go through them after the talk. So just a brief background about where I come from. So I work at CVSSP at University of Surrey. It's a Center for Vision, Speech and Signal Processing. So we have been working on creating machines that can see, hear and understand the world around them. So basically advancing the machine perception. It's a center of more than 200 people, and the area of expertise include AI and machine learning, computer vision, and so on and so forth. And mainly I've worked on the first two areas, which is AI and computer vision. So I've been at CVSSP for past 10 years. I did my PhD there, then my fellowship, and now the lectureship. And I've worked on various topics in computer vision and AI both. So the few topics are listed here. So I've worked on 3D modeling of humans. So basically generating 3D and 4D models of humans from single view images, videos, and multi-view images and videos. Then segmenting scenes, so basically identifying various objects in the scene, which includes like humans, sofa, chair, table, and stuff like that. Then registration, which is tracking of objects in the scene. So when we are dealing with dynamic scenes, we have to see how they're changing in time. So basically working with videos, that's the registration part, and the feature detection, where we do some basic feature detection, and then those features could be used for multiple applications. For example, 3D modeling, then they could be used for visual search, queries, and stuff like that. And all these techniques which I've worked on has been applied to various applications. So that includes films, entertainment, virtual reality. So I'll give you an example that we have a huge studio in CVSSP, and it's like a state-of-the-art studio with 16 cameras. So we captured multiple humans performing various actions and stuff. And then those assets were transferred to a VR movie, a short VR movie called Kinch and the Double World, which went on to win a few awards at film festivals as well. So that's the first application. The second one is this registration part, where we are tracking objects in both 2D and 3D. They have been applied to self-driving, autonomous driving, and basically that was used to track how the cars are moving in time and what objects our pedestrians are doing in time. And the third one is application to apps and broadcast production. So we have used this 3D modeling segmentation techniques and used it for personalization of media, for example, for BBC news and stuff like that. So I'll talk a little bit more about how these techniques have been used. So that was a rough, that was the highlights of what I've worked on. This is a more detailed description. So again, the aim is to increase the perception of the machines. And in that, I've worked on 3 different topics. Scene understanding. So basically understanding the scenes like humans do, right? And that has included captioning the videos, so creating textual descriptions of the videos, and then action detection. Then 3D and 4D modeling of scenes, which I'll go through in detail, so I'll leave this part out here. And generative AI. So basically creating text to images and text to videos. So using just text to generate images and videos both. Okay, and applying that to, again, multiple things, for example, in broadcast or in sign language production as well. So in this presentation, I'll go through 3 different things. The first one is 4D vision. So what is 4D vision? And what are the classical approaches? So before 2015, we have worked on 4D vision, and it was all just classical approaches, traditional optimization-based methods. And then from 2017, there was a huge raise in AI, and then all the techniques which we have been developing for 4D vision after that has been AI-based techniques, so combining computer vision and AI. So we'll look at both the approaches. Then we'll look into generative AI and LLMs and how they have been used to understand our day-to-day general life scenes. And then we'll also identify open challenges in both of those fields in the end. So let's start with the 4D vision. So when you see this video, you can understand so many things from this video, right? So you can see there is crowd, it's station, it's indoor, and people are dancing and stuff like that. But if you feed this video to a machine, it will not make sense to the machine. So how do we perceive the world? Do we perceive the world in 3D? That's the question. No, but we live in a dynamic world. We don't live in a static world. So what is a static scene? So static scene is something which does not change with time. But dynamic scene elements, for example, humans, cars, they can change their location, they can change their shape in time. So we perceive the world in 4D. 4D is 3D plus time information. That's how we detect actions, that's how we interpret gestures and stuff like that. So what is 4D vision? 4D vision is creating machine interpretable 4D data from input videos, okay? And again, it can be applied to so many things. So for example, robotics, self-driving cars, AR, VR, creative industries. So we at CVSSP have applied this to robotics, self-driving cars, AR, VR quite frequently, and it has been very successful. So this is an overview of what we have done in 4D vision so far. So basically that diagram on the right hand side, that shows that 4D vision combines 3 different areas of AI and of computer vision. That includes recognition, reconstruction, and registration. And what we have done is, so we started with 4D vision, then we combined motion information and segmentation information with 4D vision. Then we exploited AI to improve the performance of those techniques. Then we detected actions and events. And all this was done from multiple view videos. But then after the advent of AI, we have done everything from a single view, and final aim is to get a video rate machine perception. So the idea is that you input a video, and in the end, you have the 3D, 4D models of the objects in the scene, you have the full segmentation, and you also know what events and actions are happening in those videos along with the textual descriptions. So you're getting a full machine perception from that input video. And again, that can be used to create safer and smarter autonomous AI systems. So this is the framework. So we start with multi-view videos as input. They can be captured with any normal cameras, with multiple phone cameras. Then we applied, so these are the traditional methods which have been used previously. I'll move on to the AI techniques later. Then we applied some optimization framework in it to get an output something which looks something like this, which is the 4D scene reconstruction and segmentation. Now, so this 4D vision has been classified into 3 parts. The first one is creating 3D videos from input, then going from 3D videos, attaching temporal and time information to it to get the 4D models, and then using that 4D vision for scene understanding. So you start with multi-view videos, go towards feature detection. These features are used to create sparse 3D models of the scene, and then we get the 4D models. Then once you have this models, you can apply semantic data to it and also apply motion information to get the full scene understanding. So I know the slides will be available later on for all the attendees. That's why I've added some papers at the bottom. So if you need more information on how these methods are working in detail, you can look into the methods. So this is how. So now scene understanding includes the 3D, 4D model, the semantic data, and the motion information. And here is an overview of what it could look like. But what was happening is that when we were feeding it videos of like 100 frames, it was working fine. But when we work with long videos of maybe 1 minute, 2 minutes of 1,000 frames, then the tracking, the motion information was failing. So to tackle that problem, we introduced keyframe detection, which you see in the middle here. Can you see my mouse? Yeah. So this keyframe detection. So we detected keyframes across a long video, and then we also optimized the method on human pose, so that the human pose is tracked for the whole long video, and the whole optimization is based around that. So what it helped us to do is to get a full 4D model of long videos, not just short videos. And then we also extended this method to multiple people. So dealing with people who are interacting with each other, and these colors, they actually represent how the 3D information is being tracked in time. So we assign the color to the first frame, and by the time you have reached 120 frame, that color information is still intact. So when the object has rotated, the color information is still intact. So that's how we are showing the tracking in 4D. So now again, all these methods which I explained until now, they were all classical approaches. And from 2017, we started working on ML models. So now instead of inputting multiple view videos, we only input single view image or a single view video. So in this case, in this case, we input a single image with multiple people, and an ML model was used to estimate these results. And in this case, we input a single video and we applied ML model it to get a 4D model of that particular human along with the texture information. So this is the first method. So I will not go into the whole details of how this is working, but the idea was to segment each person and then create a 3D model and then also estimate the locations of person in 3D. So until this work was published, all the methods, they generated 3D of multiple people or a single person, but it looked okay from front. But when you look from the top, the reconstructions were displaced in space. So this was the first method to generate spatially coherent reconstructions. That means the reconstructions look okay from the back and the front both, and the top view as well. So yeah, this is what it meant. Then this was the second method where we input a video of a person and we trained a voxel regression network including some temporal consistency loss in it, and generated not just the geometry but also texture of the human. And the geometry and textures both were conditioned on time. So you got a 4D model rather than just a 3D model of the person. So now the problem with both of those methods that they were data hungry. We required a lot of data and it was not available online, especially the ground truth data. There is very limited ground truth data available to train the 3D models. Like if you're trying to train a method to create 3D models of people, that is not available. So we created data sets like synthetic data sets with single image and multiple image. So we created huge data sets of 10,000 images or more than like 20,000 images for both these methods. And once we trained the models, we realized that when we were running these models on real data set, the performance was poor. So then we refined our models on small real data sets to get the improvement in performance for the real data sets as well. Now, I was talking initially about the machine interpretation, right? And I talked about action detection. So these are two examples of what we have been working on. So the first method basically works that you input video and then you can identify what is happening in the scene. So for example, a person is making a sandwich, putting groceries in, putting a bag and stuff like that. And this particular method took only video as input. So we extended this approach to multimodality, where we just not input the video, but also the audio information. And what we noticed is that after inputting both the audio and video information, the performance of the method improved a lot. And we trained in a weakly supervised way so that we don't need a lot of ground truth data to train these kind of models. Now, this was all about 4D vision and scene understanding and event detection and action detection. Now, I'll move on to the generative AI and LLMs part. So, when we are generating captions of videos or when we're generating textual descriptions of videos, what is important is that we want to work with realistic day-to-day scenes and not some very restricted, limited kind of scenes. We want to identify objects and actions, and we also want to capture the spatial and temporal dynamics in the video. So what was happening is that in existing work, when we take an input, and the caption which was being generated was very, like it was grammatically incorrect or semantically incoherent, and some of the major information was missing from that. So what we have done is we combined 3 different semantics together into a captioning network. And the first one was visual semantics, where we just used the visual information of the video. The second one was the linguistic semantics, where we used 4 different parts of speech components. So the determinant plus subject, auxiliary verb, and determinant and object. And these parts of speech components were then aligned with the visual data and the global semantic. So the global semantic generated caption for the whole video instead of considering information per frame. So we combined all these things together to generate much better captions, which were basically we like evaluated these captions against like 5 or 6 state-of-the-art models, and it worked quite nicely compared to the state-of-the-art methods as well. Now, this particular work was applied to BBC data. So the plan is to use this to create media for BBC content and then personalize this media for audiences. So
A woman is sitting in a chair.
The outlook for Sunday
so we applied
to
this
Tuesday.
to a weather forecaster data set which was captured in
A
the
woman
studio.
is sitting in a chair and drinking
whatever
from a cup.
captions were generated, we converted those captions to audio. So this can be very easily used for people who have accessibility needs, right? Who
Sunday
cannot
will be a PIMS
see.
day, dry
So
with sunny
that's fine.
spells and a break in the clouds. Monday will see
And whatever
another day
events are
with
happening in the
sunshine
video
and a
will be
few showers
decoded
in the
into
afternoon.
the audio.
A woman is standing in front of a table and a cup of coffee.
So
A man standing in front of a chair.
So this particular looks like, this example looks very simple, but we ran it on much more complex videos and much more complex instances as well, which is shown on the right hand side. So if you see here, right, the ground truth caption, 2 men are wrestling, and here people are wrestling. So actually the captions which are being generated from this particular work are better than ground truth in lots of cases as well, because it gives for example, even this case, right, a person is on the motorcycle on the streets, and here you can see that person is riding a motorcycle, which gives a better context to this work. So the next part in LLMs, what we have worked on is audio visual question answering. So earlier we were only looking at the video data. Now we are looking at combining audio, visual and text data all together, encode that information, and then apply cross attention across these different types of information to get the final output. So the text modality is used as a query, and this is what the results look like. So when you are exploiting both audio and video information, so this is the question we have. This is our method, the CAD one, and this is the state-of-the-art method in audio-visual question answering. And in this particular work, the issue which we were trying to solve is that when you are inputting both audio and visual information to these LLM networks, the information is imbalanced, right? So when you are inputting audio data, it's just a few KBs, but when you're inputting video data, it's huge. It's in order of KBs, or sorry, in GBs and MBs. And when you input this data to a network, it biases itself to the video information, which is what we are observing here. So in this video, actually there was a sauna which was being played at the back. But because the existing work was biased towards the video information, it generated trumpet as the output. But actually the output was sauna. And we balanced this information using this contextual block here. Okay. So again, as you see, even here, there were 2 people, which was the ground truth, and the CAD, our model generated a better output as well. Then, so this was the LLM. Now we are looking into generative AI. So in generative AI, we have worked on creating text to videos. So in this particular work, so this was done in German, that's why the German caption. So you had text German input. We created poses from text and then meshes from text. So the idea was that if you have a caption, you want to generate a sign language output of avatars automatically, this method could be used for that. So, and then you can generate these avatars, and actually the performance was quite good compared to the existing state-of-the-art methods. Then this work deals with generating text from images. So this is our text input. And what we wanted is to condition this system on pose. So we wanted to generate images of humans, multiple humans, and we want to define how the poses of the people should look like. So we also input pose information into it, and this is what the output we get. So the man was wearing a sweater with a multicolor long sleeve. The lady is wearing a white long sleeve dress, and this is what the poses should look like. So these are the outputs which we generated. Now we also wanted that this particular work could be edited on the fly. So instead of just inputting the poses, we have input a simple model, a 3D model of human inside this, and this could be edited, like we could style the textures and we could style the fashion style. I mean, we could change the fashion style of the humans as well. So this particular work, the second work has used diffusion model, stable diffusion, and the first one has used the normal diffusion model. Again, the methods are mentioned here. This is is it playing? So this is a quick This is a quick demo. I don't know why it's not playing. Okay. Okay, it's playing now. So we created an app of the second method, and what we are doing is we are defining what type of styles we want for each person, and we can also change like the image styles we want, the hair styles we want, and we can get the final image. So I'll just play it again. And you can edit as much information you want. You can not just talk about the colors, you can talk about the styles, short sleeve, long sleeve, dress. So you can just include lots of information here. So I think I will skip this, the whole thing, because I think you get the idea of what we have done, and move on to the open challenges. Okay, so although we have looked at so many methods now for 4D vision, generative AI, and LLMs, there are still lots of open challenges in these fields we are trying to solve. So for 4D vision, the very complex scenes, right, with multiple people, like if there is a crowd of people, for example, this cricket stadium, right? If you're trying to 3D model or 4D model this cricket stadium, it's going to fail. The current techniques are going to fail. Similarly, like if you have very dynamic backgrounds, trees, waterfalls, those things cannot be reconstructed at the moment. Then there is a huge problem of lack of data to train the ML models. So if you're trying to solve more complex problems, the limitation of the data is still a huge issue. And then these methods still cannot deal with humans interacting with other humans. Like for example, this room where people are sitting on chairs or maybe interacting with each other. These kind of scenes still cannot be modeled in 3D or 4D. For generative AI and LLMs, they're still limited to simple scenes. For example, when you're generating text to images or videos, very complex backgrounds cannot be generated when you're dealing with people image generation as well. Again, the lack of data sets. And in LLMs, there is the causal information which is being generated. So when you're generating the captions from any videos, the causal information is missing. And now our next work is towards getting that causal information within the textual descriptions themselves. And again, when we're working with multimodal information, audio, video, text together, there's still a lot of mismatch between this information, and this research area is still open on how to align this information together to generate more cohesive output. Yeah, thank you.
Wow, it's kind of blowing me away a bit, that one. And I'm not clever enough to ask you a question, so I'm going to pass to someone. Brilliant.
Really interesting, thank you. I guess the first thing I thought about while I was watching that, particularly the sort of fashion builder thing, was whether we might end up with sort of custom training data for individuals that maybe like on a fashion site, you would be able to enter your kind of key, sort of training data for yourself, and you'd be able to do things like see clothing on yourself on the website. What do you sort of see in the future about, brands leveraging this tech? And, is that something that would be do you think that's something that will happen?
So yeah, actually it will. So I roughly talked about it in the previous slides as well. So once you have trained this huge model with existing data, what you can do is refine this on your own data. So when brands if you're working, for example, if you want to adapt this particular technique to your brand, then what you can do is refine that method on just a small set of data which comes from your brand information. And we are also looking at self-supervising techniques where if you feed like, okay, if you just feed an image of what we want to style it to, the network should use that information in the best possible way, that little information in the best possible way, and self-supervise to train on that. So yeah, and actually there has been like, people have been using control nets now to generate like more complex backgrounds, train from less data as possible. So we are also looking into those techniques.
Thanks very much for a great presentation. I think one of the beauties of human interpretation is we look at the same thing and interpret it differently. So going back to the previous conversation about personas, and you just raised about causal information, do you think you could ever overlay a persona into that video to text? So for example, a persona interested in bird watching might see something and say, there's some people walking through a field, there's some trees, etc. Whereas someone interested in sport might say, there's some people walking towards the green, he's 2 under par, tricky putt.
Yeah. So actually, yeah, that's a very good question, and we have been looking into that as well. So the how the models are designed is that you have some input and some output. But what people have been looking into is, for example, you take a transformer model. They have been looking into conditioning those transformer models on extra information which you could feed to the network. So the persona side of things, you could actually use that as a condition on the network itself. So you don't have to pre-train or train the network from scratch to include that information. You can just condition the network on it and then just feed information when you are doing the inference. So yes, that could be done.
Yeah, first I can't wait for you to use it on VAR and the offside rule. But my real question is, like, I've been blown away by trying the new Oculus with augmented reality, where you're not just in a virtual environment, you got cameras. And what do you think will come in terms of augmented reality with your technology?
So actually there was a small image, can I go back to my slides? So there was a small image in one of the slides which I envisioned this to be like, there it is. Okay, so this image, right? So what is happening is, I don't think so small. So you have a phone and you're observing the scene, but you're not just observing the scene. You have all the information about the scene there. For example, you can see what people are doing, right? How many humans are there, and then you can interact with that environment as well. And all this is happening in lifetime environment. So whatever techniques we have been working on, they are slightly slow right now, like they're not video rate. So the aim is to achieve this. So when I put a phone here, I can get as much information about the scene as possible. For example, this person is doing this, and this person might be doing this. So you can even predict what will happen in future, or you can see the trajectory of humans in future, and generate like textual description of what is happening in the scene. So all that could be done.
So you would use it
and
for ethnography?
Sorry?
For ethnography, for understanding behaviors and...
Yeah, so for ethnography, yeah. And then, so not just understanding the current behavior, predicting the future behavior as well. So this could be easily applied to security, for example, or maybe to survey techniques. And gaming, very important, gaming. And then, it could be applied to, again, this personalization of media, where you could have like live concerts in AR and VR. So.
Okay, last one.
Hi, that was a really great presentation.
Thank you.
If you were to look into the future, how long will it take before you can look at a video and tell if somebody's telling the truth or making it up?
Telling the truth or making it up, I don't know. Maybe I think we are not near that at the moment. It should take around 5 to 10 years, maybe, depending. So I think so. The problem is that if you want to evaluate how the model is performing, you need data from human itself. And either if we are talking about semi-automatic system, right, where the human can input information, then it becomes a different story. But if you want everything to be automatic, this is going to take slightly more time.
Armin, thank you very much for coming and
Thank you so
sharing what
much
you've been
for
doing.
this
Really
opportunity.
appreciate it. Thank you.